Well, take a moment to congratulate yourself because you made it all the way to class 4 in our series on regular expressions in Python. In this class, we'll talk about even more complex examples. We'll talk about splitting, substituting, and search and replace. So buckle in, here we go. So picking up where we left off in class 3, we're going to be back into the wonderful world of named groups. Our objective here is to find double words in a sentence. So another Python extension that we have is this $P equals name. This indicates that the contents of a group called name should again be matched at the current point. The regular expression for finding double words that you see right here can also be written using a named group, and this is the syntax. So let's dive into the code. We see P equals re.compile and our pattern. First we have the boundary marker /b, then we have our named group called word in this case. Then we have the pattern in the named group, which is /w plus, which is any alphanumeric characters one or more times. Then we have a space not inside a group. And then we have this Python extension that we talk about here, this $P equals word, and again the boundary marker /b. Our string is hello, how are you? Are you doing okay? Tell me how you're doing today. Then we have variable f equals p, our pattern, dot find iter, the find iter method, and we pass it that string 1. Then we have a for loop for match and f, print, string formatting, dot format, match dot start, and match.group. So we're looking for the starting position and we're looking for the return value that this regular expression brings back. So here you see that we have the RR, UU, and me, all the double words. This is a very easy way to trap double words. Note here that in the non-named group way of capturing double words, you'll see the /1. We haven't seen that before in this series. /1 matches the contents of the group of the same number. Groups are numbered starting from 1 on, left to right. For example, dot plus sign /1 matches the, or 55, whatever double word, if you will, that you would see in a string. Our challenge here is to find the name of all files inside a text file. So up at top, we see the text file that we're searching on. We see our code. Again, this happens within the context of a file, not through Python Interactive. We import re. We have our pattern, which equals re.compile, \w plus, \period, \w plus. So this simply takes one or many alphanumeric characters, then a literal period, which we have to escape with the \, because of course a period on its own would be a meta character, and then again a cluster of one or more alphanumeric characters. So with that, we open our file, which is called file_names, no extension, as in file, for line, in file. Our variable output equals pattern using the find all method. We pass it our iterator in the for loop, which is line, and for match and output, and we output match. And you see to the right hand side here that we're going to extract all of those that match our pattern, which would be anything that has a cluster of alphanumeric characters, a period, and another cluster. So foo.text, bar.exe, test.py, etc. It works. And in this exercise, we'll build on what we just covered, except for the fact that we want to exclude any files that happen to end in txt from our search. So it's the same file that we're searching on. We're going to start to look at assertions, right? And in this particular case, a negative look back. So look ahead assertions are available in both positive and negative form. Positive look-ahead assertions. This succeeds if the contained regular expression, represented here by the ellipsis, successfully matches at the current location, and it will fail otherwise. That is to say, it'll fail if it doesn't. The negative look-ahead assertion, this is the opposite of the positive assertion. It succeeds if the contained expression doesn't match at the current position in the string. So our code, re.compile, \b, our boundary, \w plus, which is one or more alphanumeric characters, a literal period. Then we have a group here, which is our negative lookback, the question mark, the bang, then txt, and then we have our \wt. So I had to add the \b, the boundary, to capture file names at the beginning of the lines. So it's the same thing in terms of our with statement with open file, file2.txt as in file, and it outputs, you see, all of our files, the same as on the previous slide, except for those that end in .txt. And in this challenge, we want to extract only the phone numbers from a given file. And you see in this file, we have first name, last name, and phone numbers. So let's look at our code. We see our pattern. I think it's fairly easy to understand this one. It's a \d, then in curly brackets 3, which means I want exactly 3 numbers, then followed by a literal dash. Then I want another 3 numbers, followed by a literal dash. And finally, I want 4 numbers. So your typical US phone number. And then the with statement to open the file, that's all stuff that we've seen before. I won't go into that again. You see that we do extract the phone numbers as we want to. But let's take a deeper challenge here. What if some of the numbers have the dash and some don't? How would you change the code to make it work? So let's look at our code down here. So we have the \d, then we have the 3 in curly brackets saying I want exactly 3 numbers. Then we have the dash followed by the question mark, and the question mark says I want 0 or 1 of the thing that precedes it. Right? So if I want 0 or 1, I can take it either way. And we do this for all of these. And when we do that, we see that we're able to now extract phone numbers that are listed both with dashes and without. So it worked. And in the spirit of trying to expose you to some typical use cases, this particular exercise will build on what we did in the previous slide, except for the fact that we want to extract all Social Security numbers instead of phone numbers. So it's very similar in terms of our pattern. \d with 3 numbers in curly braces after that, and then we have a space. Then we have \d followed by 2 in curly braces. So we want 2 digits there, followed by a space, and finally 4 digits to end our pattern. And you see in the code snippet to the right that we extract exactly what we thought we would from the text file on top. In this challenge, we move in a slightly different direction. Here we want to grab specific chunks of text. Our objective is to grab the start of a sentence, which includes a specific keyword, including that keyword and through the period of that sentence. Specifically, we want to grab the entire sentence if it has the word Snoopy in it, regardless of its case. So let's look at the code. We see here now we're going back to using groups. We have one group that starts with a \period followed by a \s plus. So what does that mean? The \period is capturing a literal period followed by the \s plus, which means 1 or more spaces. Then we have another group. That group is .star. .star is telling us to match 0 or more repetitions of any characters except new lines. Then we have a literal word Snoopy, which is our keyword. Then we have the \s star, so 0 or more spaces, and \w star, which is 0 or more alphanumeric characters, followed by a literal period. Now we take a look at our string, and in our string we see quite a few sentences, and of those sentences there are exactly 5 that contain the word Snoopy, either in uppercase or lowercase, the word Snoopy. Then we have our variable f3, which contains our pattern in conjunction with the findAll method that's being fed string, which is our string that contains the word Snoopy that we want to extract. Then we use our for loop, for match, and f3. Match is our iterator. F3 is the combination of our regular expression with the findAll method and the string that we want to search on. And finally, we print out, using string formatting, match 1 in square brackets, and that's a function of the findAll method that actually translates into the second group, and we've explained that previously. So it does work. If you look at the code output, I know it's rather small, but if you count it up, you'll see that we have exactly the 5 sentences that we would expect to have. Now we're building on what we just did, and instead of just extracting the sentence that has the word Snoopy, we want to do some more. We want to grab the sentence before the one with our keyword Snoopy, the sentence with the keyword Snoopy, and the sentence after the sentence with the keyword Snoopy. So we want to grab 3 sentences here. Okay, so to the code, we're going to dive right into looking at our regular expression pattern. It is by far the most complex one we have to date. So the first thing we see is that we have many groups. Let's count them up. We have 1, 2, 3, 4 groups. Okay? So the very first group we have is a period plus and a backslash period. So the period matches any character except new line. The plus matches one or more repetitions of the preceding expression, which is the period. And then the backslash period is literally meant to match the period itself. So it's no longer the meta character, it's actually the period. Okay, that takes care of the first group. In the second group, we have our backslash S plus, right? So we know that backslash S is a space, and we know plus says matching one or more repetitions of the space. Then we have the period star. The period, again, just like we saw, matches any character except new line. The star is different than the plus in that it matches 0 or more repetitions instead of 1 or more repetitions. Then again, we have the literal period, and then again we end with the backslash S plus like we started with. The next grouping is identical to what we've seen before. It is the dot star Snoopy. We have the backslash S plus, the backslash W plus, the backslash period. We've already explained that in the preceding slide, so I won't go through that again. But now to catch the sentence after Snoopy, after the sentence with the word Snoopy in it, we have the backslash S plus. Then we have in a character set backslash W, backslash S, and that's followed by the plus sign, and the plus sign says match one or more repetitions of the preceding expression, matching as many repetitions as possible, and that's followed by the literal period. So let's really dive into these groups. The very first group we have, this one here with the period plus backslash period, that would capture the first sentence, which says, here's my first sentence. We don't want that one. We only want the one that precedes, the one that contains, and the one that's after, the one with our keyword Snoopy. So it's that second group, this one here, that's going to capture the sentence that starts with sentence 2. Then this third group that is searching for the keyword Snoopy that we also want. And finally, the one right after that, the fourth group that we want, that will capture the sentence that is directly after the sentence with the word Snoopy that says, yes, I love him. So if you look down here at our for loop, we have 3 separate print statements to make it easy, and we're calling them out. Sentence before is match 1, which translates, of course, to that second group, right? But using 0-based index in this case. So the 2 becomes the number 1. Then the third group, which becomes the number 2 in our match, and then the fourth group, which becomes the number 3. So if you look at that, it proves to be successful because we look at in our code output box down here, and it gets us exactly what we need. This by far is the most complex regular expression that we have seen to date, and probably that we will see through the rest of this series. This objective here is simple but clever. We're going to use the find iter method to find positions of each time either word from a list is used in a string. So we see here we have list 1 in our code. It contains both the words Snoopy and woodchuck. We have our string 1, and then we use our find iter method with the Python join method. We see we use the pipe, and in Python that's going to create the phenomenon of either or, A, B. So it says, okay, every time you find either A, which would be the first element of our list, Snoopy, or B, woodchuck, print it out. That's what our match statement is saying, right? So you see here down below, we find the span, and again, span is the start and the end positions of the match, and the match is actually what it matched. So as you would expect, it's either going to be the word woodchuck or Snoopy. Now we examine the split method, a very useful method. The split method of a pattern splits a string apart wherever the regular expression matches, returning a list of the pieces. So the syntax of the split method is as follows. Split, then the string, and then the optional max split. By default, it's 0, but you'll see we'll use this here in the third line to say we want to split 2 times. So we have our regular expression that tells us that we want to split on anything that is not alphanumeric. That is what the backslash uppercase W does. It's the opposite of the backslash lowercase w, which is alphanumeric. And then one or more occurrences, right? So my search string is this is what I want to split, all in caps with a hyphen in between or a dash in between for the first line. The second line is the same, except that it has spaces instead of dashes. And the third line is the same as the second, except that I am now forcing the max split to be no more than 2. And then I have my 3 print statements there. And it says from search 1, and I give it the variable search 1, and from search 2, variable search 2, and the max 2. So you get to see what those look like. So before we get to the fourth and final example, let's look at the output for these. So from search 1, this is what I want to split. You see takes those things, takes the words, and removes the dash. Then from search 2, it does exactly the same thing, right? You would not know that that was different in the code from the output. Now for search 3, that's where I'm explicit about my max split 2. And you see what the output gives you here. This is, it reached its max limit, so it takes everything else and throws it into the last section. So you actually get 3 sections. But that's how the max split works. Now finally, we have this other piece of code down at the bottom. Same regular expression, backslash, uppercase W plus. However, take note, it's in a group. And this is the only difference we have here. When you put it in a group, it also prints out not just those characters, but it will print out what the delimiter is as well. Right? So you see in the first case, it's ... and in the second case, it's, .. and then we have the ands, etc. So that's the difference. If you want to be able to see the text you're extracting plus the delimiter, you must use it in a group. Okay, and we finish up this fourth and final course with search and replace, talking about the sub and subn methods, respectively. The sub method will allow you to find text and replace it with other user-defined text. It returns the string obtained by replacing the leftmost non-overlapping occurrences of the regular expression in the string by the replacement. If the pattern isn't found, the string is returned unchanged. You see the syntax here for sub, replacement, string, and then an optional count. The optional argument count is the maximum number of pattern occurrences to be replaced. Count must be a non-negative integer. So this will limit it. If you only want to replace it 1 time or 2 times or 10 times, you have the option to do that by making use of that optional argument count. So if we look at the code, it's very simple. We have dogs, cats, or fish in an OR configuration in a group. And then we have our replacement, which is animals in the second line of code. And then we have our string. Dogs are furry, cats are tricky, and fish are pets too. So in theory, if this works, what will happen when we print out replace is every time it sees one of the words in our regular expression, meaning dogs, cats, or fish, it will replace them with the word animals. So if you look down here at the code output, the very first line, instead of having dogs are furry, cats are tricky, and fish are pets too, it's going to change those words to animals. So let's see, animals are furry, animals are tricky, and animals are pets too. Ah, it worked. Second line, very similar to the first line, except we're forcing the count to 2. So now, what would we expect? Instead of all three being substituted or replaced by the word animals, only the first two will. So let's look. Animals are furry, animals are tricky, and fish are pets too. So it did exactly what we would expect. Now we get to the subn. Now subn, the method does the same except it returns the tuple. It will also return the number of replacements that were performed. So here we have it in a tuple. Animals are furry, cats are tricky, and fish are pets too. Because our count is 1, it shows 1, and it only replaced 1 time. Animals, right? Cats and fish are there in their original form. And our final example, more search and replace here, but with a twist. We are searching the string captured in text 1, and we want to replace the misspelled word animals that appears before a string in open and closed curly braces with the correctly spelled word animals. Our regular expression starts with the incorrectly spelled word animals, followed by the pair of curly braces. Then in those curly braces, we have a pair of parentheses, which represents a group. We want to match what is inside this group. Inside those parentheses are a set of square brackets, which represents a set of characters or a character class. The pattern inside those square brackets are, in order of appearance, the caret, which when inside the class instructs to not match what comes after it, which is a literal closing curly brace. So match anything but that closing curly brace. That pair of square brackets are then followed by a star, which instructs to match 0 or more repetitions of what's in the character class or the square brackets. Finally, verbose, which we haven't seen before, must be included. Verbose means that white space can be used to lay out the regular expression in a more readable style, and mostly used to add comments, which can be included. If our replacement is a string, any backslash that's there is processed. Our replacement is animals, and then in curly braces, \1. The curly braces \1 is needed to instruct us to use the group, or to instruct Python to use the group we have in our regular expression. If we did not use verbose mode, it would be looking for a literal one instead. So try this out for yourself, and you'll see, without verbose mode, it doesn't work. But with it, just as we have it constructed here, we see that our code output is exactly what we would expect. We're replacing the misspelled word animals with the right word animals, and you see it there. Well, folks, this has been a lot of fun for me. Thank you for taking this journey with me on these 4 classes that represents regular expressions in Python. Hopefully we'll have an even more advanced class in the future. Leave your comments. Tell me what you thought. I love to be able to improve upon what we have here. So let me know, and we'll see you in another class coming up soon, I hope.